Okay, so today we are going to get into our first substitution reaction on the benzene ring. So notice up until today we've been really focusing on the structure of benzene. We are definitely ready to do reactivity. And the first type of reaction we'll do is electrophilic aromatic substitution. Then we'll do sort of a little cluster of reactions to those substituents that we added. And then we'll do nucleophilic aromatic substitution. So we have kind of three main groups of reactions to cover involving aromatic compounds. So we'll be spending quite a bit of time on this. To start off, we're going to use something we know to try to understand why, if we tweak it a little, we might need to tweak it some more to actually get the desired effect. So alkenes, as you recall, have a whole bunch of reactions they can do. Like, for example, you can brominate an alkene. So let's look at that reaction. So remember Br2. You might actually remember a solvent like carbon tetrachloride being explicitly written over there. Not entirely necessary, but pretty common. Remember that reaction? Bromine was added. We used that was a verb, added to the pi bond. It's a technical verb. It means we did an addition reaction. So what that means is there were H's there, right? And the H's are still there. So you can draw them in if you want. And the bromine came in, the Br2, and one went on the back and one went forward. So they had the anti-orientation. So we had the enantiomer as well. Because it could have just as easily been the bromine on the top being the wedge, bromine on the bottom being a dash. So this is racemic. Okay, so that's something we know coming into this. That's an old reaction, so I'm not going to harp on the mechanism, although it wouldn't be bad to go back and review it if you're unsure. But remember what we were doing here. The H's were still there, so we did not remove an H, we removed a pi bond. So this is called addition to a pi bond. And so if I just sketch out the very first step of the reaction, we saw that bromine, which is usually described as nonpolar, can have an induced dipole as it approaches the electron-rich pi bond to have the delta plus and delta minus, so that the electron cloud is distorted in the presence of another electron cloud. And so that means that the pi bond can attack the less electron-rich region of the bromine. And we can get that to leave. And then we had that bromonium ion intermediate, right? So that lone pair, there's a lot of lone pairs in bromine, right? But one of the lone pairs comes back and reattaches itself to the other carbon. So we have that three-membered ring, the bromonium ion intermediate. Our important point comes right here, as we are noticing that we have the alkene attacking. The bromine is the electrophile. So it is, that first step is to attack that bromine. So this is an electrophile, right? If we try, well, we say, okay, well, benzene's electron rich. Why were we told to not do benzene reactions with the alkene chapter? If you try, there's indeed no reaction, which we write as NR. So in other words, what would it look like if we tried to do it? Let's just say we had one equivalent, and we're going to only take off one pi bond, just like the other one did. And let's just draw one of the enantiomers possible. That's what we would have formed if we were able to get bromine to have undergone addition reaction with Br2. What is wrong with this product that it doesn't want to form? Well, remember benzene's aromatic? This is no longer aromatic. So it doesn't form. So you can write a little X, usually it's even a red X for emphasis, over the arrow to say that doesn't proceed as written, or write NR for no reaction. However, we know that benzene's not the only aromatic molecule. We have substituted benzene rings throughout the textbook and natural products. So they have to be able to have reactions. And that will be the case. In fact, there will be a lot of them what we could do. We just need a little bit, as we'd say, a hotter electrophile, but also maybe a different mechanism, a different approach. So what comes to the rescue here is the addition of a Lewis acid, FeBr3, to the mixture. We will indeed get the reaction we are imagining. So notice that we did not do an addition to a pi bond. The pi bond's still there. What did we actually do? That H is gone. So we did a substitution reaction. It's a different class of reactions. So here, I'm summarizing that here. Simple alkenes do addition. Benzene did not react with some of those reactions that simple alkenes do, like addition, because addition destroys aromaticity. Let's bring this up a little. So that's why we saw no reaction. But if we were to add a Lewis acid, FeBr3, it makes a stronger electrophile for us. And by the way, I'm going to be abbreviating electrophile because we'll use that word a lot, as E+. So what that does is it helps weaken the bromine-bromine bond. It's easier to break, and we can still get a product that maintains aromaticity. We only add one bromine, so we don't add both. So we replace an H instead of replacing a pi bond. In fact, we'll be able to do this with a number of reactions. Actually, before I do that, I'm going to actually show how that works. So when we have the bromine in the presence of the Lewis acid, like that's a kind of an important question we don't want to skip. What's special about that FeBr3? By the way, you might also see AlBr3, right? So they're both transition metals, and they are both the aluminum and iron are both electron poor, happy to accept electrons. That's what makes them a Lewis acid. So look at bromine's covered in electrons, and we have FeBr, which is known to have a very low electronegativity, very happy, in other words, to accept electrons. So that's what a Lewis base does. So let's label those. Lewis base gives electrons. Lewis acid takes them. So we're not talking about a proton transfer. That's specifically Bronsted-Lowry acid-base, right, terms. However, all Bronsted-Lowry acids and bases are Lewis acids and bases. So just refresher on that. Okay, lone pair attacks the Lewis acid. Okay, then we form this complex where we have bromine on the end, the one that didn't do anything. The one that reacted lost a lone pair and made a bond to iron. Iron already had a bond to 3 bromines. That ends up giving it a negative formal charge. You can calculate that for some practice. And the problem is that we have a full plus now here because we have 2 bonds to bromine. You might also want to verify that formal charge if you're not sharp on that these days. So net neutral, however, notice that before we had a delta minus, delta plus, just a induced dipole on bromine. Now we have a fixed charge on bromine. Much more reactive electrophile. This is our electrophile that we will be using in the mechanism. So you have to create the electrophile in situ, which means like in the solution, Latin for in the solution, in order to keep going and finish the reaction. So we don't write it over the arrow like this because it forms in situ. Let's put that here. All right, so this is our electrophile. Very strong. Need a strong electrophile to get benzene to react, because we will see in the mechanism it has to temporarily lose aromaticity, but it gains it back. So the cost isn't that great. It's just that activation energy is still pretty high. Okay, so we will learn 5 such reactions where this is the case. So here's kind of the general summary of what we'll be covering. I call them Electrophilic 5, sounds kind of like a music band. And what you want to be comfortable with is visualizing how they're going to react with benzene ring. So I'll give you the name of the reaction and then the electrophile that formed in situ. And that's like the key electrophile to use in the mechanism. And that's just for summary, but we'll treat each one in detail. So we've already kind of looked at bromination. We haven't done the full mechanism yet, so I'll go through that in a minute. But it doesn't have to be just a bromine. It could also be a chlorine. So we could have added chlorine or bromine. So I'll write that here, Cl2 or Br2. And we could have FeX3, like FeCl3 matches with Cl2, FeBr3 matches with Br2, but it could have also been the aluminum or AlBr3. Those are common Lewis acids that are kind of interchangeable for this reaction. So we halogenate the benzene ring, and that's a halogenation. So if it was bromine, we call it bromination. If it's chlorine, we'll call it chlorination. So I'll just generically write it as halogenation. The electrophile, as I wrote before. So when you're ready to do the mechanism, you form this first before the benzene comes to the party. This has to happen first. Okay, so we will also learn about adding a nitro group. We call this nitration. And this will be what the electrophile resembles by the time we are using it for setting up for electrophilic attack. Excuse me, nucleophilic attack from the benzene ring. We can also do sulfonation with that. And ultimately, we'll get an SO3H on there. But we start off with SO3 in the presence of acid. And we put a sulfonyl group on the ring, but it's reversible. So we can actually take it off with acidic water. And then these two are very important, carbon-carbon bond forming reactions. So if you want to make a carbon-carbon bond with benzene, these are going to be the ones we go to. So they're famous reactions named after the scientists as usual. So another name reaction to add to your list, Friedel and Kraft. So it's Friedel-Crafts. And these are both a form of Friedel-Crafts, and I'll point out the difference in a second. When it's only an R group, like an alkyl group, simple R group, we call that alkylation. And it uses a carbocation as the electrophile. So when the R group has a carbonyl immediately attached first, so we have our halide, so this is alkyl halide. We have our halide, then we have a carbonyl, then the rest of our R group doesn't have to be methyl, by the way, like ethyl or something else, so I might just write R here. We call that acylation. You're adding an acyl group. And you can think of the carbocation once again like this, that we are using as our electrophile. Okay, so it's going to share these mechanistic steps, all 5 of them. That's why we're grouping them together. Their mechanism's really the same. You have to know how to form the electrophile. That's the different part. Once you get the electrophile, you insert it basically into this mechanism template. So I'm actually going to go through this slowly here, but I'm not going to do it every single time we do an electrophilic 5 because we don't have time for that. It's good for you to practice that. I would suggest you write them all out. But keep this in mind. I'm going to do bromine as my example because we just did that one. We're going to do attack of the electrophile by a benzene ring pi bond. So remember my electrophile for bromine we had formed by letting the bromine react with the Lewis acid, FeBr3. And now that makes it a stronger electrophile. And I know it looks weird, but that's required for something as stable as benzene to actually react. Okay, so if you notice, we're going to actually use a pi bond now as the nucleophile. It's going to attack this bromine. Why does it want to do that? A lot of students say, oh, it's positively charged here. It likes that. Remember, this is a formal charge. This does not mean it is lacking electrons. In fact, it doesn't have the right number of electrons distributed around it to be a neutral formal charge, 0. And so that's the driving force, is to actually liberate this bond back to being a lone pair. So now we will have the usual 0 formal charge on bromine. So we form FeBr4 still, but it lost because it lost one of those bromines. I don't care too much about the side product because what I really want to focus on is what's going on in the aromatic substrate. And so notice that benzene lost a pi bond. It's temporarily not aromatic, but its resonance stabilized carbocation is formed. Okay, so I could have picked any pi bond from the benzene ring to react. At this point, it doesn't matter. It will if there's a substituent on there, and we will do that one step at a time. But at this point, it doesn't matter. So since I picked this one, I'm committed to that. That means only one of these 2 carbons can get that bromine, and it doesn't matter which one. I could put it here, I could put it here. So where do I have some space? Right there. I'm going to put it here. That means the other one gets to be the carbocation. Because the pi bond is gone, both carbons are missing the bond to the pi bond. That means one gets the bromine, one gets the plus charge. All right, so that is resonance stabilized, and that is worth taking the time to evaluate that. So let's show that resonance. So we delocalize that positive charge around one of 3 possible carbons. Move that pi bond there. Yes, we're getting there. And if you try to keep going, go ahead and do that for practice. You'll see we're just going to go back where we start. So those are all the unique ones. This is actually called the sigma complex. It's just resonance of the carbocation, but it's got a special name because this is a very well-known mechanism. So it's something you'll want to recognize and be very comfortable with. Okay, so recap before we move on to the end. Benzene attacks this variable electrophile coming from this list up here, up above. So pick your electrophile based on what was over the arrow. The rest is the same. New group. This could have been a nitro, could have been a sulfonyl, could have been a alkyl group. But the rest, step 2 and 3, look the same for all of these reactions. So I think I accidentally used my eraser. Bromine, there we go. I think that was the only thing I erased, I hope. Okay, so we're here, and that's going to look the same. The last step's going to look the same as well. You pick any one of these resonance structures, doesn't matter which one. I'll just go ahead with the one I started with, and we re-aromatize the ring. We don't want it to not be aromatic when we're done. How can we do that? So this carbon is missing electrons. How can we re-aromatize the ring? We need a pi bond back. But what's wrong with the pi bond back? Let's draw what happened here. All the H's at the affected carbons in the pi bond that was changed. So H's were not pulled off. They're still here. If we want to put the pi bond back, we need to lose that H, not that one. This one has 3 bonds. This needs the electrons from the pi bond. This is not able to accept the electrons from the pi bond because it has 4 bonds to it. This H needs to come off. So that Lewis acid had just made a conjugate base. How convenient, right? So that's kind of what we have so far based on what we've been doing. And we're going to use this bond here to restore our Lewis acid. So if we break bromine off away from here, we get FeBr3 back. Hey, that looks a lot like what we started with, right? So that's helpful, catalyst style. And take the H, leave the electrons from the H not to make an anion. We're not trying to make a zwitterion, or even an ylid, which is what that kind of zwitterion is when they're adjacent. Give it to the bond, so we have a pi bond. That will re-aromatize the ring. There we go. Benzene ring's back. Still have the bromine on there. Final product. aromatic and all. Side products, just to note, I'm not always going to show them, but I like to the first time we ever do anything new. FeBr3 is back, and we do make HBr. How do we do that? Br went off with the H. We broke the bond here. So we had HBr and FeBr3. Those aren't quite as important as the organic ones, so those are usually not be shown. Okay, so we are going to spend the next little while going through the electrophilic 5 and then implications that it has when there's more groups on the ring. So hold on to your hat. It's going to be a fun ride. Okay, so we've covered the first electrophilic aromatic substitution reaction. Let's do the second one, nitration. We need this mixture over the arrow, HNO3 and H2SO4. But how does that NO2 get on there when we start with NO3 and H? That's what we're going to show. That's the point of the mechanism. Because we know the rest of the mechanism from the general template, right? We know how we make the sigma complex, although we will do it probably again just to be on the safe side. And I don't plan to repeat it every time though. HNO3 plus equals, let's actually write out the Lewis structure. HN, and it has O minus. It's resonance stabilized with the other O. Okay, now as much as I would love to give that poor oxygen an H from the sulfuric acid, and yes, it is very likely that will happen. I'm trying to not draw every single equilibrium pathway possible. I'm only trying to show the productive ones, and that's the point of the mechanism. So I am going to show this one, who clearly doesn't need it as badly, but that's the way we will have to eventually funnel the protons in order to get this to cooperate. Why is that? I mean, my point is I could draw this getting the H, then I draw a new product, then I draw this getting the H, then I draw this losing the H. We're going to assume that we can kind of follow that that's possible and not worry about every single acid-base equilibrium and use the ones that are beneficial to the forward progress of the mechanism. So you may want to write them all out and see why it's not efficient or useful to do that. And your book will not show you every path. We are beyond that. We're not doing acid-base. We're not doing every acid-base mechanism possible. So you're going to have to be buckle down and say, why did I leave that one alone? In reality, you're not. You can acknowledge, yes, that's going to get protonated, but it doesn't do anything to my goal. I need to get rid of this O. How do we get rid of O's? We need to go from 3 O's to 2 O's. We lose water. Who's almost to water? This one. That's why we're using this one. So then with that in mind, we let that happen. So made some water over there. Okay, so that's the driving force to get that to go. Now, if we want to show how the water's gone, we can actually use, remember this guy we really wanted to give that proton to? He can help us out now. You could push those electrons down, which means this nitrogen, oops, it already had a positive charge here. Missed it. 4 bonds to nitrogen, positive formal charge. That nitrogen cannot accept anymore. It's going to have to eject the water by water. When you want to show water coming off and kind of emphasize that, because that was the whole point of that exercise, you can put that little rewarding curved arrow coming out of the reaction mechanism. And very nice, we're left with, I'm not drawing the O's that are behind. Ha! Our true electrophile has revealed itself. That's our electrophile for the rest of the mechanism. Now you take that guy and you do steps 2 and 3 from before. I'm going to do them one more time, just for fun. We're not going to do it forever though. I mean, I'm not going to do it forever because I just know that I can't make these lectures 10 hours. So here comes step 2. We made the electrophile. So that's our electrophile. Step 2, use that electrophile to react with benzene. Okay, now benzene, pick a bond, any bond, must be a pi bond. How about for fun we do a different one than the bottom one? I did the bottom one last time. Let it attack there, right? And open that pi bond. It says that degree of freedom to do that because if it accepts the electron, it could release those. So now benzene is no longer aromatic. Predictable. It's got that carbocation that's resonance stabilized, right? So which carbon did we decide to give nitrogen to? Doesn't matter. I'm going to pick this one that's closer to me. As long as you remember, so notice that oxygen's negative charge now, single bond. That's what the red arrow tells you. As long as you remember to give that carbocation to whatever carbon did not get the nitrogen. Okay, step 3. Re-aromatize the ring after you show the sigma complex. So sigma complex. Ooh, what's going on there? Sigma complex. It's going to be this guy, delocalizing the carbocation. You should come up with 3 structures minimum. You can get more if you start getting to the cases where we have substituents on the ring. I'm going to call this NO2 now, because that way I can not write everything out so lengthily. Plus. Now let's give myself a little more space. Get to here. Red, I'm going to push the electrons one more time to get my last unique resonance structure. NO2. And there we are, down at that carbon, which is the one I started with last time. So that just shows I could have used any of those carbons because they're all treated equally. There's my sigma complex. Pick one of those to re-aromatize the ring. I'll write out as separate steps. You don't really have to. It's just going to be a long mechanism. Could fill a page if you need it to. Let's pick the middle one. Can I do that? It's actually kind of an annoying one. Why don't I like the middle one? So I'm glad I picked that out. I need a pi bond back. If I put it here, it forces that one to move. If I put it here, it forces it to move. If I put it here, it forces it to move. So the simplest case would be, where can I easily put a pi bond? It's always going to be a pi bond to the nitro group and one of the adjacent carbons. So the new group, the carbon with the new group, and one of the adjacent carbons. Since these both have pi bonds already, I'm going to choose one of these other 2. So new carbon with new group, adjacent carbon, nope, not okay, has a pi bond already. Yep, this one needs the pi bond. So I will take that one, or I will take this one. Carbon with the new group, adjacent carbon needs the pi bond. So I could take this one, I could go this way to re-aromatize the ring, or I can go this way. This one I could still do it, I would just push more arrows, and nobody wants to do that, right? So let's pick the last one. How am I re-aromatizing the ring? I need the H that's on the carbon with the new group. It's still there, remember? Didn't lose it. It's not a substitution yet until that H is gone. Okay, who did I make as a conjugate base that could come in? Well, you might say, okay, SO4 minus, NO3 minus, not really. But we gave off water as well. I would accept anything that's reasonable because it's an acid equilibrium. So HNO3 minus, NO3 minus, that's fine. H2SO4 or HSO4 has the conjugate base HSO4 minus, that would be fine. Water, since we drove off water, is also fine. So I will use water. You can only use water if you formed it or it was given. So I will write here, or HSO4 minus, or HNO3 minus, because these are conjugate bases of the acids provided. There we go, it's re-aromatized, and we, voila, have our nitrobenzene. Okay. We've learned 2 of the 5. Let's take a break and do a fun synthesis before we learn number 3. Okay. So, 2 electrophilic aromatic substitution reaction, halogenation, nitration. So we're ready to do a two-step sequence. And the sequences will get very long, so we might as well start now, practicing now, because if we learn 5 electrophilic aromatic substitution reactions, you better believe there's going to very likely be 5-step sequences. So why not start with 2? So bromine with FeBr3. There we go, we get our bromobenzene. Now we're going to nitrate our bromobenzene, because we can add groups to nitrate and halogenate, not just plain old vanilla benzene. We can add groups to benzene that's already been functionalized. So that will certainly work. A reaction will happen. The question is, what is the product? Now it matters which carbon we pick. Will we pick carbon right next to bromine? Will we have an ortho nitro to the bromine? Will we have a meta nitro to the bromine? Or will we have a para nitro to the bromine? So let's write out our products that are possible. So this would be, oh, I skipped meta. That's okay. That'll be the one I write. I usually do ortho, meta, para. It's just kind of a habit, but there it is. Ortho, para, or meta. Doesn't matter what order. So the 1-2 scenario, the 1-4 scenario, the 1-3 scenario, what are we going to form? And you better believe it's selective. So how are we going to understand that? Looking at it right now, it doesn't make a lot of sense. We have to dive into what the mechanism looks like once the groups are attached. So I told you we'd be doing that mechanism a lot. Let's look at this again. In general, we're going to come back to this, in other words. It's going to be to be determined, okay? I'm going to make this a more general question. We could in other words, we're asking, if we have a mono-substituted benzene, how do we know where Y goes, the new group? So start with X on there. Where does Y go relative to X? And that big long line coming out of the middle means we do not define where it is. So we're not sure. So it matters. Turns out it matters what X is. X is the boss of where Y goes. Okay, so here's the rule. We need to first look at X and ask, is it an electron donating group or an electron withdrawing group? Okay, so an electron donating group has a special term. It's called an activator. Benzene is the nucleophile. It's electron rich. Electron donating groups make it more electron rich, increases the electron density. That makes it a better nucleophile. Therefore, it speeds up the reaction, hence activate it. However, if X is electron withdrawing, you better believe we're going to get a totally different outcome. It's considered a deactivator for the most part, because it will decrease the electron density, thereby making it a worse nucleophile. You're sucking electron density out of the nucleophile. Therefore, it's a worse nucleophile, slows down your reaction. Okay, so let's look at something specific again. Here's an experiment that's been done, and we have the results that we can share the percentages, and we could see where the distribution is favored. Toluene, let's start with that. Methylbenzene. What do we know about methyl? Remember we said the group on there is the boss. It's weakly electron donating. R groups, weak EDG. So it's not a deactivator, it's an activator. So it does make it more electron rich. Now, what is the effect on the distribution? What's preferred, ortho, meta, or para? So let's think about all the possibilities. I'm going to bring this down, and I'm just going to sketch out our outcome here. Statistically, if you say, here's my electron withdrawing group, there's the para position. There's one para, so this is statistically. And that's part of the equation, right? Because reactions happen by the collision. And so if there's one way to get a para product, then that's an impact. That's not going to be the same distribution as something where there's two ways to get a different product. So that actually does come into play a bit. Ortho, there's two ortho positions, right? Two ways to be ortho. So it could have done this one, but it could have equally hit the other side and landed there. So statistically, it should be twice as likely that we get ortho over para. One para, two ortho. So in other words, or this one. And yes, you can acknowledge they are the same product. That's the point actually. There's two ways to get the same product. So it's easier actually to form it when you're talking strictly about whether you would have a collision with it or not. How about meta? Let's draw out the meta. So if we have that here, our meta position would be here or here. Two meta to it, right? So once again, two ways to get meta. So in other words, we should expect, if it's statistics alone, para to be the smallest in the ratio, lowest percentage of para. Let's see what the real answer is. Para is 40%. Meta, ooh, look at this, less than 1%. So for our intents and purposes, meta doesn't form. Ortho, 60%. I'm going to rewrite the statistical predicted, statistical distribution. 1 opportunity for para, 2 opportunities for meta, 2 opportunities for ortho. Clearly, this did not match our statistical prediction. Something else is happening. Now, 40 and 60 is this unique reaction. We will often see 50-50. So we're going to treat ortho and para as if they're practically equally likely. So we're going to call activating groups like methyl ortho-para director. Now, will we always get 60-40 or 50-50? So most will be, assume most are 50-50, unless, assume most EDGs give 50-50, unless sterics are in the way. How will sterics play a role? They always can play a role. Sterics can play a role because this is closer, right? So if we had something bigger than a methyl, like maybe a T-butyl, bromine would be less likely to fit over here, and then our ratio would suddenly probably reverse, like 60-40 instead of 40-60. But we still get both, so keep that in mind. But if you want to dominate one or the other, you can actually use sterics to your advantage. Okay, so why is this happening? That's kind of the golden question. What I urge you to do is stop this video, write out the mechanism that we just did for the reaction we just did with it substituted now, and see where that carbocation lands. See if one of the products, you're going to have to write out 3 mechanisms. See if one of the products favors one over the other. We're going to ultimately do that together in a different example, but you might want to even do it with this one. So we're going to kind of build up to that. Okay. So we'll pause right there and see you soon.